Hi everybody. Here we go for lecture 24. We're getting about halfway through this second half of the course. The first half at home in Furman, and the second half now wherever you are scattered all over the country. Hope you're all doing okay. Hope you're all feeling good about what's going on. It's a hard life we're living out there, but you're doing what you need to do. So here we go with lecture 24. Section 31.1 to 3 is actually a pretty short sections. This is a lecture where I typically do a fair number of demos in class. I guess I didn't notice that when I set the syllabus up. So it's going to be a short lecture today. That's okay. You're probably not going to complain. Okay, so the two quiz questions. Here's the true-false question for a change. Just as a changing magnetic field, changing and it's understood in time, time change, changing magnetic field in time produces an E field. Does a changing E field produce a B field? Well, I think you guess that that's true. Otherwise, we wouldn't have asked the question. This part is Faraday's law. Faraday's law says that if I have a d by dt of a phi sub b, then I take minus that, and that gives me the induced electric field. That gives me an EMF. Okay, and we know what that's integral E dot dl. So this goes the other way. Suppose we have here a d by dt of phi sub e. Do we get a magnetic field? And the answer is yes. And that gives us what's called Ampere's law, which is one of Maxwell's equations, but it's the generalized Ampere's law, generalized Ampere's law. And that's one of the answers for what are the Maxwell's equations. And it should really say generalized, because the Ampere's law we have so far is specific to not a time change of electric field. What are the other Ampere's laws? It's these three here. Faraday's law, Gauss's law for electricity, and Gauss's law for magnetism. Those four equations are Maxwell's equations, okay? And they are the fundamental set of equations for electricity and magnetism. Mechanics has Newton's laws as the fundamental equations. E&M has these four laws, and they form the basis for everything that happens in E&M. So this set of equations is actually what your author calls section 31.3. There's nothing in that section except writing down these four equations all in one place and talking about them. So rather than put them at the end here, that's the 31.3 part of this. So what are they? They're Gauss's law for electricity, which we've done way back when at the beginning of the course. I've been saying this kind of all along. We'll say a few words here. Gauss's law for magnetism has no source term because there are no magnetic monopoles, so that's that one. Here's Faraday's law. Time rate of change of B gives me an electric field. And we're going to show here today what the generalized part of Ampere's law is. Up until now, we've known only this much for Ampere's law. Integral of B dot dl is how much current goes through there. Now we add this term, and that gives us the whole story. Look at the structure. Look at the structure for these equations. We have two surface integrals, integral E dot dA, integral B dot dA, and two line integrals, okay? They're coupled equations, They're coupled equations. This one stands alone, and this one stands alone. But the integral of E dot dl depends on the time rate of change of the magnetic flux. But the magnetic flux determines integral of B dot dl, okay? This thing couples with that, so it's a closed loop kind of system here, and that's what makes this set of equations so interesting, okay? What is the generalized Ampere's law? Okay, well, here I kind of already said a lot of these things. Here's Ampere's law so far, as we've written it so far. Back in chapter 28, that was actually the first, that's interesting, that was the first lecture for this Away from Furman online experience, This doesn't seem that long ago, or it seems a long time ago, depending on how you look at it. Generalized Ampere's law says if I had a current flowing through some region of space, if I take that current through that loop and integral B dot dl around that, I get mu naught I enclosed. That gives us Faraday's law, which is there, which produces an EMF. What about the inverse? Does a time rate of change of E give me a B? And the answer is yes. Now, look, the picture your author has here in the book for this argument is a lot better than mine. Okay, so I encourage you to look at that picture, and his discussion is pretty good too. But I want to say a few words about how we might implement this. This says, suppose I take a circuit that looks like this. Let me make sure I'm on screen. I'm going to take a battery here, plus and minus. I'm going to connect that with a resistor, and I'm going to connect that around to here, around there. And I'm sorry, I should have put a switch in here. Okay, when I close that switch, current flows around this loop. I should have made this plus and this minus. I'm sorry, I'm not going to restart the video. I got the polarity wrong. That makes a current that flows this way. Okay, charges this plus minus, and over an RC time constant, I get a time rate of change of current. Okay, that makes an electric field here because these two parallel plates make this configuration a capacitor. All right, let's use Ampere's law, integral of B dot dl, with that I enclosed, where that I is this I right here. Okay, if I take a closed loop around here, okay, then I get a time rate of change of current, which gives me a V field that gives me a value for magnetic field there. Okay. However, if I can move that shape around in space, okay, that would say I'd have a B field all around this wire here. I'd have a B field all around this wire here, but in the gap between there, there's no current flow. Okay, that would say the magnetic field intensity would drop to 0 in between that gap and come back around again. That doesn't make sense. Okay, so the argument is that there's going to be some new kind of current, okay, where this current is the true conduction current, okay, the actual physical placement, and we're going to add this new kind of current called the displacement current here that, if you want to think about it, is kind of patching up the equation to make it mean continuous, to give us continuity in the magnetic field. That argument is kind of what we're going to do, okay. So here's the argument, and it's kind of straightforward, that those two parallel plates are a capacitor. The charge is the capacitance times the voltage. Now you got to remember a whole bunch of things from earlier in the course. Remember what we saw for a parallel plate capacitor. Q is C. Here's the capacitance for a parallel plate capacitor, epsilon naught times the area over the gap for this capacitor plate, the area of those plates, and that gap D there between those plates. The voltage is the electric field times the distance. Remember that for a parallel plate capacitor. So put those two things together, and this D cancels that D, and you simply get a real simple result that says the charge is epsilon 0 times the area times E. Okay. Now, what is the current? The current is dq dt. Remember all these fundamental things, huh? Hopefully this is coming together. So dq dt there, that's a constant, that's a constant. So dq dt is just dE dt. So it's like a kind of a current, which is epsilon 0 d phi sub E times dt, okay? Because if I write this as epsilon 0 d by dt of E times A, A is a constant, so I can pull it through there. Well, that's just the flux, okay? So that's what I get there, that current. Well, what do? We say that in this part of the circuit where there's wire going through there and real current flows, that's what Ampere's law says, mu naught I enclosed. Where there's no current flowing, we get this new term that we have to add there, which is a kind of a pseudo current or a fake current, which we call a displacement current, and it looks like that. So that's the true current, the conduction, that's the true current, the conduction current, and that's the displacement current. And that's the generalized Ampere's law. Let's take a specific example for charging a capacitor, okay? And here we're going to change, so I'll take that same circuit I did before with a parallel plate, I'll make the resistor go to 0, and for the sake of argument, we're going to make it, instead of a square plate, we're going to make it circular plates. That makes the argument we make a little bit easier to do from symmetry, okay? Here's the resistor that goes inside there, okay? So here's an R, and here's a C, and here's that same argument we just made before to derive the equation, and we're going to do it now for this particular example. Here's the result from the previous RC circuit charging thing. That's the capacitance, that's the current, and so on. And look, I'm not going to belabor this. You just follow all these arguments for this particular example. I'm looking at the magnetic field inside that gap there, where there's no true current, okay, but there is a displacement current. How much is it? Integral of B dot dl is just B times dl over a closed loop. So that's B times the circumference of that circle times that term there, and that gives you the magnetic field value. Here's the top view of that thing looking down, okay? So you might have a tendency to say, big whoop, what's the point of all this? Oops, I realized I forgot to move the page up there, okay? Here's the result you get for the magnetic field. And you ask me, what's the significance of this? What's the practical value of this? Sorry, ladies and gentlemen, this is one of those just kind of theoretical things that, unlike much of what's going to follow here later, doesn't really have direct tangible applications. Okay, here's the second of the short sections from this from today's lecture. And it's really, if you want to think of it as a derivation of Gauss's law for magnetism, that may be a little bit too overblown. Here's what we did for Gauss's law for electricity way back at the beginning of the course. Integral of E dot dA was Q enclosed over epsilon 0. We had, for charge enclosed, we had all the plus charges and all the minus charges. And if we took the sum of all those things, there may be only plus charges, we get one result. There are only minus charges, we get another result. Maybe more of these than these, and vice versa. That's the answer. If you do that same kind of argument for the integral of B dot dA, then instead of the charges, we would have a term for the isolated magnetic north poles and the isolated magnetic south poles, okay? But remember what we said, you can't have those. You can't have those. Here's the physical argument, okay? Electric field, we can have a monopole or a dipole. For a magnetic field, we can make a dipole out of a loop of wire, but there's no such thing as a magnetic monopole. So what's the answer? The answer is integral of B dot dA is 0. Okay. That's it, ladies and gentlemen. That's the end of this, this section here. There are a couple of simple homework problems to do from this section. I would have you look at those. Look at the problem questions as well for this. I hope you're working on your project course proposals. Some of you started to send those to me. Most of you must be working on them because I haven't heard from you, but I'm getting a few questions here and here. So I've got a Moodle, I've got a Zoom meeting coming up with you here in about a half an hour, so looking forward to that. Hopefully you'll have some questions. Ladies and gentlemen, take care of yourself. Contact with me if there's anything I can do to help you along with this stuff. Adios, and stay healthy and stay safe. Bye-bye.